Welcome to the realm of the zeroth root. First, let's get the basics down. The square root of 4 is 2 because 2 squared is 4. The cube root of 8 is 2 because 2 cubed is 8. And in general, an nth root of a number a is defined to be a number x, such that x to the n is a. In other words, x is the nth root of a. This is probably a concept pretty familiar to us, but gets a little hazy when we start to consider the zeroth root. That's where n equals 0 in this situation. Let's see why with a few quick examples. By definition, 2 to the 0 power is 1. 3 to the 0 power is also 1. In fact, any positive real number to the power of 0 is always defined to be 1, not the original number. So the zeroth root doesn't make sense in this way. If we apply the rule from before, we would expect that the zeroth root of 1 is 2, also the zeroth root of 1 is 3, which is clearly not consistent. How can the zeroth root of 1 be both 2 and 3 at the same time? It doesn't make sense. Yet we're not ones to back away from a mathematical challenge. Let's try another approach to this issue. Remembering that radicals are simply another notation for exponents, maybe we can find our way to the zeroth root. For example, the cube root of 64 just means 64 to the 1/3. The square root of 64 just means 64 to the 1/2. The first root of 64 is 64 to the 1/1, and so the zeroth root of 64 should be 64 to the 1/0. And herein lies another problem with the zeroth root. We're dividing by 0. And since dividing by 0 is also traditionally undefined, we can't say what this is yet, but maybe we can get close. We can use the tool of limits to express our roots as a function, a number to the power of 1/x, and allows us to vary the root and approach 0. Let's get closer and closer to the zeroth root and see what's happening. And as this limit problem indicates, as x gets smaller and smaller, we get closer and closer to this idea of a zeroth root, the overall quantity gets larger and larger. In fact, we're going out to infinity. So does that mean that the zeroth root of x is infinity? That might seem like a sensible definition, albeit unconventional, but there's another problem. We did this example for 64, and we're going to get a similar result for real numbers larger than 1, but what if the number we're taking the root of is less than 1? Let's say a is between 0 and 1, and now consider this same limit. And in this case, the limit is 0. As we get closer and closer to this zeroth root idea, the overall quantity gets smaller and smaller towards 0. And so suddenly defining the zeroth root as infinity makes less sense because it depends on the value of x. And so you may be tempted to define the zeroth root of x piecewise, like this: infinity if x is larger than 1, and 0 if we're between 0 and 1. By the way, if x equals 1, you probably just want this to be 1 itself. Yet there is another issue. We were only taking this limit from the right for values of x larger than 1, but what if we approach from the left for values of x less than 1? And if we do this left-hand limit, things seem to flip. The example with the 64 now doesn't go out to infinity, but tends towards 0. And if we're looking at values between 0 and 1, the opposite happens again. Now this is blowing up to infinity. And while sometimes on this channel I like to give intuitive, albeit unconventional definitions to these sort of things, in this case, with all of these wild results and all of these different conundrums, I think it's best to leave this idea of a zeroth root how the mathematical community has done it, which is undefined. But there is a very, very famous number which is traditionally undefined that I believe should not be. This is the most controversial number in mathematics, and here's what I think it should be. Click the video on the screen to check it out. I'll see you in that one.